Hi everybody, this is a second related rates video for you. Over the weekend, you're to finish that half sheet on the related rates. There were 6 problems. Right before I give you that other example I was talking about, I want to give you a couple hints to start some of the problems because I know when you're at home doing them by yourself, it's a little bit harder to do them. You might not feel confident in what you're doing if there's no one else to ask. So before we go to your notes section, you could title your notes related rates number 2. I'll be doing another example for you, but let me jump over here and just get you started on a couple homework problems to make sure you do them right. So again, this is on the half sheet. On the half sheet, most of you got to number 1 and number 2, so I'm not going to do much with those. Some of you got to 3, some of you hadn't started 3 yet. So number 3, I just want to make sure you use the correct formula, because if you use the wrong formula, then obviously everything's going to be wrong. We have a circular oil slick caused by a spill of 1 cubic meter of oil. Whenever you hear cubic meter, you don't want to think area. You want to think volume. So some of you I saw started the problem using area and you were using this formula because you thought it was just a circle, but you don't want to do that. That would be square meters. If it's cubic meters, then you want to use volume. What's happening here? So what's happening here is we have a blob of oil that spilled, and over time the blob of oil spreads out and it's much less tall. So on your drawing, you want to do a circular thing that has a height. It has thickness. The next problem I want to talk about quick is number 4. So in problem number 4, we have a circle. They're talking about a radius, and we want the rate of change of the area. So if we're talking about area of a circle and they give us information about radius, you're ultimately going to be using this formula. But before you can use that formula, you're going to need to solve for radius. You don't know what it is. Radius is subtle information. They tell you the circumference is 20 pi. So you should use the fact that circumference is 2 pi r. And then you can solve for radius. You can get the area. Those are both subtle things that you need because they give you the circumference. And then you can get the rate of change of the area. That's what I want to do. Yes. So then you can keep going with the related rates problem. The last thing is for problem number 6. There's a lot of parts in number 6, but there's not too much math involved. It's just because 6, we're doing a problem like this in class. The cone problem is a lot more difficult than the ones on this sheet, and I want to make sure you understand how the proportions work. So we have a cone like this, and if a cone is like this, it's upside down. I know period 5, some of you thought this is a right side up cone, but in problems like this, if a cone is upside down, it's going to look like this. And part B asks you to draw the water height. And just so you draw your triangle right, part C asks you to draw a right triangle, and it needs to be like this. This is the right triangle for the entire cone, and that's the slant height. And then in part D, you're going to need a right triangle for the liquid's height, which would be like that. So you can finish that problem and do the proportions. The problem that I want you to add to your notes is this one right here. It involves angles and theta and trig functions, which is why I didn't show it to you right away, just because it's a little bit more difficult. There's more things to consider. So go to your notes after the last related rates notes and write this example down. We have a boat. It's being reeled in at a rate of 1 foot per second from a point 10 feet above the water. So as soon as I hear a rate, I'm going to think d something dt. This is what I'm looking for. At what rate is the angle between the line and the water changing when there is a total of 25 feet out? So these are numbers they give me. Those are things I can put right into my table. All these guys. There's other information that's subtle that we're going to have to find. Ultimately, I want to find the rate of the angle, so that rate of change. There's a little visual here to help you see what's going on. So let me get this boat moving here. So here's a boat. It's being reeled in. Here's the line that they're using to reel it in. And as you can see, at the last second, the boat seems to move a lot quicker. Remember, the rates of change are not constant throughout the entire problem. They change depending on when you stop the time and find the rates of change. So we want the angle between the water and the line. That would be where my mouse is right now. They give us this information. Ignore the numbers they give you here. This is just for a different problem, but the visual is the exact same. So we want the angle here, that rate of change, and they give us the length of the line as well. So let me go back to here so we can actually solve it. So all the math I'm doing, I'd like you to do. I'm going to do this one live rather than have you just copy it and it's pre-written because it'll be easier to follow along with. So you should always draw a sketch first. And what they give us is that this is 10 feet. This we don't know. This we know, that's 25 feet. And we know the rate of change here. It's -1 foot per second. Now think about why it's negative. It's being reeled in. So here's my little boat. And here's the water. The boat's getting closer and closer, so the length of the line is getting smaller and smaller. Ultimately, what we're looking for is the rate of change of the angle. So here's the angle. With the angle, there's a related d theta dt. That's all they give us right now. So let me go ahead to step number 2, which is to do all our variables listed out. So write your table down. We have x, we have y, and we have z. I'm going to go ahead and call this x, call this y, and call this z. It's easier for me to remember y being up and down. I know some of you made this length y, but I like this one being y. We also have another thing going on here. We have a theta. We didn't have that before. For every single variable, I'm right away going to put the rate of change with it so I don't forget. For whatever variable, you need the d dt. So, and then there's d theta dt. I'm right away going to put my question mark right here because I want to know what is the rate of change of the angle. Theta, I don't know. Z is 25. Y is 10. X, I don't know, but it's subtle. I can get X very easily. If I have two sides of a right triangle, you can get the third one using the Pythagorean theorem. We'll do that in 1 second. Dx dt. I don't know dx dt. I don't know the rate of change of the boat in the water. Dy dt. Okay, y is the height here of the thing that's holding the rope that's reeling the boat in. As if you remember from the animation, the boat was moving, the line was changing, but this height wasn't changing at all, so that's 0. Dz dt, I know that, that's -1 feet per second. Let's go ahead and do the Pythagorean theorem quick to get that piece of subtle information. And you can go ahead and do the steps here. You do 25 squared minus 10 squared. You get x squared equals 525. So then x is the square root of 525. So I'm going to put that right here. I'm going to keep it as a radical just so it's not rounded and it's a more perfect answer. Okay, so there's this theta going on here. I don't know what theta is right now, but if we have a right triangle and we know all the sides, all you have to do is use trig to get theta. You could get any of the thetas. So if you really wanted theta, you could set up a little trig ratio here. How about we do sine? You could do any of them, but I'm going to do sine because it involves the pieces of information they gave me. And that would be sine of theta. So sine of theta is 10 over 25. So that means sine inverse of 10 over 25 would be your theta. Sine inverse of 10 over 25 happens to be 0.4115. I just typed in sine to the -1 on the calculator. And this is in radians. We're not in degrees anymore. In calculus, we're really going to stay in radians. The next step, we got our subtle information. So this was definitely a subtle piece of information. We need a formula that relates all our variables together. If we had just done a problem that had a table like this, then we could definitely use a Pythagorean theorem. And you did a problem like the ladder problem, you use a Pythagorean theorem, you are good to go. There was no angle. But we can't use that right now because we have an angle and we have to have a formula that involves sides and an angle. Well, that means we're going to have to go to trig, and you could technically use any trig function that you wanted, but I'm going to use the one that relates the pieces of information that they gave me. That's usually how I approach it. Again, you could do cosine, but I'm going to go ahead and do sine. If I do sine and I set up a ratio for it, you know that sine is opposite over hypotenuse? Well, opposite is my y. Hypotenuse is z. Notice there are no numbers yet. Don't plug in for your variables until after you differentiate, or else you're going to completely mess this up. The next step is to find the derivative with respect to t. So I'm going to do d dt of each side. So derivative of sine is cosine, And that was the outside. The derivative of the inside, that would be derivative of theta with respect to t. Now right here, I have a quotient, so I should be doing quotient rule here. So I have bottom ho d high, that would be dy dt, minus high d ho, all over denominator squared. So you might be thinking this is going to get really ugly because there's a whole lot going on right here. But what I like to see is there anything that I can completely zero out? And that is my dy dt, which is 0. Now notice there is no dx dt in this table. And in fact, I kind of ignored it right here. I should have talked about this earlier. But dx dt, if you wanted dx dt, you would have to do a completely other related rates problem, and then you would have to get dx dt that way. Then you could keep going. But the thing is, we don't even need dx dt. So this is kind of a question mark for another problem that we don't need. So dx dt is completely irrelevant here. It's not even in the problem I'm doing right now. So that's why I completely ignored it. This is the real question mark we want. So let's keep going here. Cosine theta, I'm just going to rewrite it so it looks a little nicer. Cosine of theta times d theta dt equals negative, don't forget that negative, dz dt all over z squared. Remember, we ultimately want this guy by itself. You could divide each side by cosine of theta. I'm not going to do that quite yet just because I don't want to start a whole complex fraction. Cosine of theta, don't think having to do cosine of inverse or anything like that. You know what cosine of theta is because remember this is theta. Cosine of theta is just the ratio adjacent over hypotenuse. So I'm going to replace cosine theta with what cosine of theta is. Root 525 over 25 times d theta dt, that's my unknown, equals negative y. Well, y was 10, because that's the height of the thing reeling the boat in, times dz dt, negative 1. I'm plugging right into my table because that's the next step. I already differentiated. Now I plug everything in. Z was 25, and I'm squaring it. All you have to do now is just kind of type things into your calculator, and you can do this. This is just arithmetic right now because we only have to get d theta dt alone. On your calculator, you should do, this is 625, 10 divided by 625, and then divide that number by root 25 over 25. D theta dt will ultimately end up being 0.0175. The thing is, we need a unit here. Like, what is the units for the rate of change of the angle? We know it has to be per second, something per second. It's not going to be feet because this is an angle. Angles, remember, in calculus are radians, not degrees. This is the rate of change of the angle right here at the moment when z is 25. If you were to stop time at any other moment, like let's say when z was 20 or 15, the rate of change of the angle would be different because remember, when the boat reeled in at the last second, it seemed to speed up a little bit. So make sure this example is completely written down. If you need to watch it again, go ahead. Hopefully you were able to follow along. We'll do a problem that has to do with a cone. That was homework number 6 on that half sheet, and then we'll do another theta problem. Have a great weekend.